So remember, sine phi is going to be a constant here. I need to integrate e to the rho times rho squared. And to do that, I'm going to use integration by parts. So I think at this point I'll leave you to this to take it the rest of the way, because we've done triple integrals already. This is really just a matter of converting to spherical, making sure you get all the pieces of the integral set up properly. Yeah, I'll let you have that. All right, let's look at the next example. Oh, well, actually, that's the work for it. Don't worry about that. And then that's the homework assignment. You know what? Since that's all I have to talk about with this, and there's some more videos with examples, let me go ahead and work this one out. I'll go ahead and do that. So I want to do the integral of e to the rho squared d rho. And I know that I have a sine phi here, but I'm going to ignore it because it's a constant. What I would do is I would set up integration by parts. I let u be equal to rho squared. I'll let dv be equal to e to the rho d rho. And then du is 2 rho d rho. And then v would be equal to e to the rho. So by the formula for integration by parts, this will turn into u times v, so rho squared e to the rho, minus the integral of v times du. So notice I have a 2 there. 2 rho e to the rho d rho. And I can pull that 2 out. So I'm done with this for now. Pull the 2 out. Rho squared e to the rho minus 2 integral rho e to the rho d rho. And I have to do integration by parts again. So u is going to be rho. dv is going to be e to the rho d rho. Du is equal to d rho. And v is equal to e to the rho. All right, so now what we do is this piece right here, which is just this right here in brackets, is going to turn into this times this minus integral of this times this. So I'm going to try and write that over here. I have rho squared e to the rho minus 2 times, in brackets, rho e to the rho minus integral e to the rho d rho. And the antiderivative of e to the rho is itself. So this just becomes rho squared e to the rho minus 2 times rho e to the rho minus e to the rho. And then I can distribute. So going back to this triple integral, here's what I know. This is equal to integral 0 to pi over 2, integral 0 to pi over 2, and then that inside piece, the antiderivative of this, is all of this. I'll distribute the 2 through in a second, but remember I had to assign phi there. So it'll be, I'll just put the sine phi here, sine phi times rho squared, e to the rho, that's this, minus 2 rho e to the rho, and then plus 2 e to the rho. And I'm evaluating that from rho equals 4 to rho equals 9. And then I still have d phi d theta. So I've got to replace all my rows with 9, and then all my rows with 4, and then subtract. So let me try that. This is going to be integral 0 to pi over 2, integral 0 to pi over 2. All right, let's plug in 9 for rho. I'm going to have sine phi times, all right, 9 squared is 81, rho, e to the rho, but rho's 9, so e to the 9th, minus, let's see, 2 times 9, 18, e to the ninth again, and then plus 2e to the ninth there. That's what I get when I plug in 9. Then minus, again, sine phi, and then plug in 4. So 4 squared, 16 e to the 4th, minus 4 here, we get 8 e to the 4th, and then plus 2e to the 4th. All right. d phi d theta. All right. This should simplify a little bit. Integral 0 to pi over 2, integral 0 to pi over 2. All right, sine phi. And then, let's see, 81 of these. 81 plus 2 of them is 83. So 18. 83 minus 18, right? 83 minus 18 is going to give you 65. So we get 65 e to the ninth. I'm going to write it this way. 65 e to the ninth sine phi minus over here, you get 16 of these minus 8. That's 8 of them plus 2 is 10 of them. So 10 e to the 4th. 10 e to the 4th sine phi, like that. And then d phi d theta. All right, that looks okay. Now we integrate with respect to phi. Excuse me real quick. Okay, so we're going to integrate now with respect to phi. Notice also that 65 e to the ninth minus 10 e to the 4th, these are both constants. So what I could do is this. I could just factor out a sine phi like that, right? We'll move it over a little bit. Factor out that sine phi. That'll be a little bit nicer to integrate. Just be one integral to worry about, one antiderivative. So like that. And now antiderivative of sine of phi is going to be negative cosine phi. So integral 0 to pi over 2 times negative cosine, well, yeah, cosine. I'm just going to go a little faster, but I'll just do this. This is all a constant, so it just came along for the ride. I'm evaluating this from phi equals 0 to phi equals pi over 2. Then d theta. So let's talk about what cosine, let's plug in pi over 2. Cosine of pi over 2, right? Cosine of pi over 2 is 0, right? So that just zeroes out, the whole thing zeroes out. And then we plug in 0. So I'm getting 0 when I plug in pi over 2 minus, now let's plug in 0. Cosine of 0 is 1, but then it's negative. So it'll be negative 65 e to the ninth minus 10 e to the 4th and then I'm going to integrate that with respect to theta. So all that happens here is that this minus and minus become a plus. The 0 doesn't matter, so it's really just this. And you're integrating it, that's a constant, right? So you're integrating constant with respect to theta. We should just get that number, 65 e to the 9th minus 10 e to the 4th theta, that's the antiderivative of that, from theta equals 0 to pi over 2. And of course, when we plug in 0, we don't get anything, but when I plug in pi over 2, it's all of this times pi over 2. So the answer should be 65 e to the 9th minus 10 e to the 4th, all of that times pi over 2. And that should be it. Now I'm going to double check that because I think I did do that with the computer. Yeah, they went in and simplified it a little bit, but this is the answer right here. So if I take this and distribute it to each one of these, I'll get 65 e to the 9th pi over 2 minus when I distribute here, the 10 and the 2 reduce out, you get 5 e to the 4th times pi. So that answer matches this one, so we feel good about it. That's basically it. Now, for your homework, again, look at those problems that I had assigned there, and you'll get some practice. The difficulty, I think, most of the time is just first getting the correct region, all right? So you'll see in the homework how that works out. And that's it. That's all the notes I'm going to give you for spherical coordinates. Okay, we're going to talk about Chapter 12, Section 8, which is change of variables. And there are lecture notes online, but I'm going to try and simplify everything here with a picture. What we're doing is we're taking a double integral over some region R, and this actually extends to triple integrals also, but it's easier to draw a double integral region of integration than it is to draw a triple integral region of integration. So with that in mind, we have a double integral over some region R. Our variables are x and y. And we look at this double integral and we say, okay, maybe this region of integration is very challenging. Maybe we can't represent it easily as in Cartesian or polar. Maybe it's not a type 1 or a type 2. So we're having some trouble with this region. Then what we want to do is change the variables to some new variables and hope that that new region, when we switch over, is easier to integrate. The other reason we might want to change variables is if the function we're trying to integrate is difficult. If this is tough to do, then maybe if we switch it to a new function of changing the x and y to some new variables, maybe that new integration is easier for us to handle. So that's usually the two main motivations for doing a change of variables. So what we have to assume here is that we are going to have some way of determining what we're going to change the variables to. So I know that I can switch my x over to some function of u and v. That way all my x's get replaced with something, right? So my x is going to become some function of u and v, which I will call x of uv. So x becomes some function of u and v, and also the y, everywhere I see a y, I'm going to change that to a function of u and v. Now these functions don't necessarily have to be the same. So what I'll do is I'll just replace x over here with some function of u and v, and y with some function of u and v, and then I should be able to integrate over this new region. But the big thing from the big idea here from change of variables, that when you do this change of variables, we don't just replace dA with dA. We have something else happens here. So the idea is that you take some infinitesimal region in here, right? And we need to know the area of that. So that has some area to it. I'll call it dA because it's infinitesimal. And when we switch it through this transformation, because x and y changed, that little dA also changes. And what it turns into over here is going to be what's called the Jacobian. So this is, I'm just going to put a capital J here to represent the Jacobian. And then we'll have, with respect to the two variables, u, v, or you could, depending on what the region looks like, you could have that, those integration variables switch places. But this Jacobian, what it does is it's kind of like the give and the take. You're allowed to switch the variables over to something new, but you may have to multiply these differentials by something to make the scaling of the region over to this, either the shrinking or the contracting or the deforming of that region. To make it work, you've got to have this factor in here of j. So what is j? That's the next natural step, is to ask what is j. So before I can begin that, figuring out what j is, let me just talk a little bit about an example, I guess, to kind of show you from Cal 2 that you were actually doing this before. Okay, so I'm going to show you a simple result. Let's say we were trying to integrate in Cal 2 something like x cosine of x squared dx. So if we were doing something like this, what we would realize is that if we let this be u, this is almost the derivative of it. So we make a substitution. U is x squared. We differentiate. Du is 2x dx. And then we could say half of du is x dx. So we would rewrite the integral. This cosine of x squared would become cosine of u. And then x dx, right here, turns into 1/2 du. So what I want you to notice is that I have changed the variables over, right? I've switched from here a function of x to over here some function of u. So I have made a change of variables, but my dx did not become just du. I had to scale it by 1/2 in order to make this work. So that's what you did in Cal 2, but you didn't really realize at that point that this right here can be generalized more into double integrals, and that we need a way of coming up with this number. Now in Cal 2 it was pretty easy, we could see how to do it here. But here in Cal 3 we need a more general formula for it, and that's what we're going to do here. We're going to establish that formula. But there's one other thing that I need to review with you, and that's this thing called determinants. Now determinants, this is a very general thing. A determinant is a very general thing. It can be used in many, many different applications in many different math courses, engineering courses, physics courses. But the computation for a determinant is pretty universal. So what we do is we start with a matrix, and we're gonna look at two types here. Let's say we have a 2x2 matrix. So we have a matrix. It has 4 numbers in it. Now these don't have to be numbers, they can be a lot of different things, but for us these are either going to be numbers or functions. So we have a 2x2 matrix, and we put these bars on the side to represent the fact that we are going to find the determinant. So when we do the determinant, this is an algebraic computation. We do a times d minus c times b. CB. And that's it. That's the determinant of a 2x2 matrix. Now, if we do a 3x3 matrix, it's a little different. A 3x3 matrix, we'll have to label this. Let's say it's A, B, C, D, E, F, G, H. I guess I'll use I. That's fine. How do we find the determinant of a 3x3? So what we do is we start by looking at the top left, okay, and we write that down, A, and we multiply A times a determinant.